Hello everybody, my name is Christian. I'm a member of the mursat project team and would like to present our project today. As you can already see in the title, mursat is a hackerspace arts project. What does that mean? Actually, it started off as an arts project only. I work for mursat, which is a small ISP, and to start with that's the plan, what we would like to do. We would like to shoot this thing to space, like 300 kilometers above the Earth. It's the original size, so it's really that small. What is mursat back? Mursat is a small ISP for arts and cultural organizations in Graz, in Austria. And we're also making a lot of projects involving arts and technology. So we thought a satellite would be very nice to have. We started it like 2 years ago. The first thing was that Jogi Hofmüller, one of my co-workers, read the news that there is a company in the US. It's called Interorbital Systems. They have a very special offer. They offer you a kit, a satellite kit, including the launch to LEO orbit for $8,000, which is very cheap. Normally this costs like $40,000 to $100,000 depending where you buy it. And we thought, okay, that's definitely doable to make an arts project for it. So we started to get funding for it, and we wanted to participate in this space thing, something we thought it could be Space 2.0 after the 60s, where all this space magic, and now it's Space 2.0 kind of. And we wanted to be part of it. So we got public funding and bought the kit. And when we got it, we thought, okay, that's a lot more work we anticipated. And so we started to get new members in our team and read lots of stuff. The first ideas, even before we had the kit, we thought of things we could do with the satellite. One of the first ideas was we wanted to build a radio scanner. By this radio we mean FM broadcasting, like radio stations. We wanted to listen to the radio stations from space, wanted to know which radio stations we could receive in space, and even, if possible, receive multiple stations at one time, because they share the frequencies, but they are not near on the floor, but of course from space they may be nearby. And wanted to listen to this radio and see what is leaving the Earth. Then we wanted to make a ham radio relay, of course. We wanted to send messages to the Earth back, so ship up some messages there and send it back. We also wanted to send messages to space, something like you shout into a microphone on Earth, and then there is a loudspeaker in space. Of course, there's no air, but we found it funny to send something to space, a message. One early idea was laser graffiti, so mount some laser diodes on the satellite and blink back to the Earth. But there's already somebody in Korea, I think, who does it. We wanted to have like an idea how the satellite feels in space, how it flies through space, if you will. And therefore we wanted to know how the tumbling goes on, because the satellite it's not stable. It will be released by rocket, and afterwards it will tumble over all axes. And we wanted to know what is the speed of this tumbling and how does this feel. We actually thought about a machine mounting some guys in a revolving thing where you can tumble with the same speed as the satellite does in space. And also we thought of a very good idea. It's called poor man's space travel. Of course, the team members will take part of it, and also you can buy poor man's space travel. You can give us a hair for $250. We will bring it to space. If you want to be part of it, just get to us. Okay, so as I mentioned earlier, we bought this kit and it came like in the normal post box. It took some time because the custom took some time to get it to the custom. But we finally got it, and then we looked at it and yeah, we thought, okay, that's less than we anticipated. We thought that would be more in it. What you can see here is the solar panels, microprocessor unit, it's actually an evaluation board, which we don't use because it's crap, and battery, some metal, the ejection cylinder, a sample ejection cylinder. This is actually a part of the rocket where the satellite, the actual satellite, will be put in on the rocket and pushed out in space, and some software. And the software is basically the Java files and PCB schematics for the PCB boards and the electronics. As I already mentioned, batteries and solar cells. And there's also, not on the picture because we got it in another way, some micro-hard modems on 2.4 gigahertz. That was the first plan how to communicate with the satellite, but soon we found out it's not a very good idea to use them because there is a lot of trouble with licenses and stuff. So we thought, okay, it would be much better to make it an amateur radio satellite. Yeah, as you can see, you need much more than the kit got here. So after some time, we bought a lot of things. We made some VCBs and bought some components and started to build it. And yeah, after some time, we found out, okay, probably that's not the best thing they got us. So we started quite from scratch. Yeah, I want to tell you now a little bit about the current plan we are working on, the current payload projects we are working on, because these early ideas, some of them turned out to be not possible to realize. We want to mount a piezo microphone on it. Of course, there is no real sound out there because there is no air. But we hope that at least some molecules will hit the piezo and we can detect that. We also want to take audio samples, like some seconds of audio, and hopefully we will hear some thermal expansion, contraction within the satellite and also in the microphone. And some sound artists already told us, yeah, that would be very cool and make some sound with it. Then there is Jupiter Larson. It's an artist from the US. He works with various counters since some years. And he told us, okay, it would be very cool if the satellite itself is, for us, the satellite is the performer, and the satellite, the artist, if you will count for us. And we thought of some things we could count, and one of the first things we can sort of is, okay, let's mount a button on the outside and make a label, if you're an alien, please press here. And yeah, hopefully this goes up, but most probably don't. What we're really counting is the number of beacons we will send out. The satellite sends a beacon at a fixed rate, and we are counting that. And we also want to count like the rotations of the satellite using photodiodes mounted on the satellite. Of course, you have to take pictures. We will mount a camera on there. Try to make pictures from space, from the moon, from whatever. Then there is another artist who would like to send kids' wishes to space. The idea behind this is that kids can, or somebody can wish, has a wish if he can see a shooting star. And the idea is to put wishes into a satellite, and when it burns up, after the mission period, it will be a shooting star on its own. So that's the idea behind it. Also, there is a group called Alien Productions. Their name is, they had the name before the project already. They did it for the European Broadcasting Network, did an arts project where they compressed the complete European culture into one small 2 kilobyte file. and send that out to space. And we also want to broadcast it if the energy budget allows it. Yeah, and of course all the data we receive and gather during the mission is freely and open available. Okay, next will be Bernhard.
Okay. Well, nice picture. It's a typical meeting of a communications group. Was normally, you've already heard, we're a group of artists and hackers. So not entirely 50-50, but this is mostly ham radios and hackers talking about the communication design. And when we talk about hackers, let's also talk about camp, because there were a lot of things we weren't unsure about because we're not experienced satellites builders. We are the hackers that the artists came to when they thought how to build a satellite. Let's ask our local hackerspace. And so at the camp we had first opportunity to actually talk with people with a lot of experience, which was very, very rewarding. So thank you, Mario. And due to that, we have also found a newfound desire in ourselves to redesign a lot of the components that iOS sent us, or the example designs, which of course, most of it won't be possible at this stage of the development. But we found out the dipole antenna wasn't that good an idea, but we're still going to go with it. We already have redesigned the power system because we have to consider stuff like what if the battery short circuits, what if the battery goes into eclipse, it goes below 0 degrees, lithium ion battery below 0 degrees breaks pretty fast, so you have to heat it. That's all things we had to consider that wasn't in the original schematics or in the kit. And of course the transceiver and the modem, we completely replaced that because we wanted a CV beacon where we could hear the satellite even if it isn't actively transmitting downlinking data to us, but something that always works, that says, oh yeah, satellite, there you are, we hear you. And the 2.4 gigahertz modem, which we originally bought, it had a lot of issues with basically, it wasn't open. It was closed black box, and everybody who wanted to talk to our satellite would have to buy that black box. That was a big no. So complete redesign. Now we use ham radio frequencies. Yeah. Also, team building, listening to satellites became a big event. You probably already saw us with the antennas out there, and it was a great way to get a feeling for how communication with satellites works. So, and this will also be a future event on our Graz-based radio station, Radio Helsinki. It's free open radio. So we will have lots of talks about mursat in the future, starting from 2 weeks from now. And also listen a bit to satellites on the radio. Yeah, listening in style, there we are. Maybe you saw us. Yeah, there's also a lot of bureaucracy going on. Mainly I'm enumerating 4 things which we have to deal with. First is the frequency allocation. It's not per se bureaucracy, because you can put the satellite up even if you don't ask them. But it would be good to have a frequency that no one else interferes with you, or even better, you don't interfere in the frequency of someone else because they can sue you. So good idea to coordinate. Then iOS itself, which is our launch provider, the people who sold us the kit and are going to put our satellite into orbit, they have troubles of their own, because apparently in the US, if you want to become a space launch provider, you have to jump to continuous hoops of tests, and you have to achieve several tests all within the same year, or at least before 2011 ends, and none of them can fail, or you have to start from scratch. So they have it pretty tough right now, but I think they're going to manage. Then, of course, you have to register the satellite somewhere. If your country doesn't provide a satellite register, you have to register with UNO. Austria didn't have a satellite register recently because the Technical University of Graz, incidentally, basically at the same time or a bit earlier than us, started to build a satellite. The Austrian government has now noticed that it wouldn't be too bad that you have to be able to register satellites as in the country. This has one big advantage for the country, because if there is no law governing satellites and there goes something wrong with the satellite, the country will have to pay. So, of course, they want to implement a law that moves all this responsibility to the actual builders. So they are pushing a law through the Senate, to the Nationalrat right now, which says we have to get a 60 million euro payout, a 60 million euro insurance. There's also some stuff in that, like already running projects are exempt, but the definition what is already running is kind of steep. Also exemptions for, the insurance sum can be moderated in special cases, but then you look in the comments of the law and it says, if we can be really sure that you have so much money you can pay this anyway, you don't need insurance, sure. Yeah? So, but basically we're a state-financed art project, so we're hoping this counts for something, and they won't throw away money they already spent for us, and we will be counted as an already running project. But just some of the stuff we're dealing with. Then, of course, launch. This is going to be on launch because iOS launches somewhere in the US or in Tonga, and we're going to package the satellite, send it to US, and this will be the launch for us. And then hopefully we will hear that it has somewhere arrived in space, packet to space. That's how it should be. No? Space Station 1, please deliver to low Earth orbit. Of course, party follows. Yes, a bit of about the environment we have to deal with, because space, you have already heard a lot about space, not that friendly environment. I mean, satellites don't need to breathe, but still. Delivery, we are going to be shot up with the iOS Neptune N45, probably. If it's certified until 10, it will carry 32 CubeSats and bit more in the inside, so it has a total payload of about 50 kilograms, and it's currently under development. And start conditions will of course be, there will be a lot of disturbance and mechanical stress on the satellite during launch, lots of vibrations, so of course we have to design our satellite to withstand that environment. Then LEO, Earth orbit, we're going to deploy it in a low Earth orbit, which is about 310 kilometers. For us, this is one of the lowest limits of low Earth orbit. And we will have 90 minutes orbit time, which means about 20.5 degrees of it we'll see the Earth. And that means hopefully we will get to see the satellite about 1 to 3 times a day, during which we can communicate with the satellite for maybe up to 10 minutes if we're lucky. Also, mission duration at this height, at 310 kilometers, you still have some atmosphere. It's not much, not enough to breathe on. Definitely less vacuum, less air than you could, than you would have in a vacuum that you create on Earth. But still, at the high speed of the satellite, it produces enough drag to drag it down at most 6 weeks. So depending on if our satellite actually makes it up there, depending on whether iOS actually can deliver, our mission time will be between 0 and 6 weeks. Can you show the video from the polar orbit so people can see a bit how polar orbit works? What does that actually mean? It means the satellite will rotate in a basically circular orbit, while the Earth will rotate around the below the satellite, and it will be pretty fast. So it moves about 28,000 kilometers per second. And that means from horizon to horizon, we get maybe 10, maximum 12 minutes time during which we can communicate with the satellite. Also, the frequencies will be Doppler shifted, so not only you have to have an antenna which points to a satellite, and you have to move it after a satellite, how you very know it is, or hopefully know, you guess, you hear the beacon, and you also have to shift the frequencies accordingly. So here, this is, we've already probably seen today, screenshot from gpredict, and a moving satellite at 28,000 kilometers per second has a small footprint from which where it can be, the area from where it can be listened to. And that area moves pretty fast. So, here you go.
Okay, I'm gonna switch over here. We have, of course, some environmental stuff we have to guard against. Of course, there is a lot of mechanical stress during the launch. The rocket will produce a lot of shaking and stuff like that. So we have to build the satellite very hard to make it withstand that. As already mentioned, there is no air, so there is no convection. So that's the main thing. Things keep cool down here, but up there, even a small chip which won't heat up here can overheat in space. So we have to take precautions for that. We have very, very broad ranges of temperatures. Our satellite will be sometimes in the sun, sometimes behind the Earth. We will lose temperature quite fast when we're behind the Earth and warm up very fast when we are in sun. Of course, we have to prevent of hardware faults and software errors. So try to program a defensive and try to anticipate what can go wrong and how to fix it. We have the transceiver drift. Probably because of the temperature changes and other environmental things, the transceivers can, the frequency which the transceivers use to transmit can drift probably too much that we will leave our allowed space within the spectrum. So we have to implement an emergency switch off where we can switch down all the radio communications in order to not jam any other signals. And what's also very interesting is the gases which may be trapped in some components in the soldering, stuff like that. For example, it's no good idea to put an electrode condensator up there because it will lose all its inner parts and will ruin your complete satellite. There are also some stuff we ignore. For example, all the things that has to do with lifetime, because we have a mission time of 6 weeks. Nothing gets old that fast. Not the solar panels, not the battery, nothing. We also ignore, in a way, the radiation. There was a talk like 2 days ago about radiation in space and calling the LEO the baby pool of radiation in space. That's where we are in, so we don't have to make big precautions because of radiation. Of course, we will mount some aluminum on the chips or stuff like that to protect from it, but we don't have to actually do a lot about it. And we also don't and can't withstand these extreme temperatures as we might have up there. So minus 40 degrees is big problem because most of the chips, most of the components we can buy don't withstand these temperatures. And therefore, yeah, if it gets that hot or that cold up there, our satellite might die. Yeah, that's okay. We have to live with that. Okay, so to the last part, to the technical stuff, more technical details. Of course, we have some constraints. For example, the weight constraint. We are allowed to lift up 750 grams there, and it's not like the limit on a plane flight where, okay, bring some more kilos, it's okay. It's really 750 grams, that's it, no more. yeah, our mechanical structure and all the numbers you can see there. At the moment we are about like 500 grams, so we have still 250 grams for hair, for example, or what we want to bring up there. Here you can see a component diagram. It's a rough schematic about the components the satellite will exist of. Very important is the so-called IHU, the internal householding unit. It's a chip that controls all the energy levels, measures the currents from the solar cells, and always knows what's going on the satellite. It measures temperatures, temperature of the battery, for example, if the battery is too low and we have to heat it, or stuff like that. We also have a DTMF receiver and a TTX is a CV encoder. These are the low-level command and control interfaces, but we will talk about it later and more in detail. We have our main processing unit. The main processing unit is the chip who controls all the payload applications we will have, like the JBAC camera, the piezo, the alien encounter, of course, and it will have some vast majority of memory attached to it, like 4 gigabytes or so. We will never be able to download all this stuff, but we don't want it to delete things because deleting in Flash needs a lot of energy. So we want to put up there a big memory, which we wouldn't be deleting at any point. We just add things. And then there is also a broader communication channel which can be used to download images and other information from the satellite. Okay. The power supply, we have like 48 solar cells mounted around the satellite. You can see these black things here. They are connected together like this. You can see it here. We have one solar cell. The datasheet says we have 28 milliampere of current coming out of the solar cell. If the light is perfect and everything is perfect, they are connected somehow that one of these PCBs will produce like 46 milliampere at 6.6 volts, and summing that all up when we think that probably 3 of those will be in sun at that one time, that will be something like 1.1 watts we get out of the solar cells. That's not very true, because we think it's more like 500 milliwatts or even less, because the solar cells are not perfect, the conditions are not perfect, not all of them might be in sun, and there is some rotation in the satellite, and probably the rotation is in a way that not all solar cells are in the sun. Okay, yeah, you can see it there. These are the solar cells. And we have some dynamic energy management on the satellite. That's because the main processing unit doesn't know how much energy the satellite has left, and that's the IHU, what the IHU is for. And the IHU controls all the energy levels, so it knows how much energy is left on the satellite, and therefore we thought of an easy protocol how to distribute this energy and, for example, give the MPU some amount of energy to do all the tasks. Yeah, as you can see, we just separated in energy tokens, which can be separated on the several components of the satellite. Yeah, people antennas, you again.
Okay. So, still a lot of time left. Well, about the antenna gain, as already mentioned, we have a dipole antenna, which means the field of Sandy, the emission field looks a bit like that. It's donut-shaped, which also means if you're here, you don't get to hear the satellite. So that's one of the problems. But one of the advantages is if you're here, you get to hear the satellite a bit better. That's basically what antenna gain is all about. The problem with that is that's all fine if you know how your satellite is oriented in space. So if you can make your satellite point a dish towards you, That's great. You get all that concentrated energy, that antenna gain towards you, where you are, and you hear the satellite. In our case, we don't have the weight budget for any kind of attitude control, and we also don't have the time, because even though the attitude control systems, which take up a lot less space and weight, they take some time to stabilize the satellite. So basically we do nothing about that, and we're stuck with the dipole antenna from design with iOS, which means we could get in the unfavorable position where we are here and the satellite rotates like this and we never hear it. So that would be worst case. Best case would of course be it will always look down, probably not gonna happen. What's probably going to happen is that we will have fading, so sometimes the cone of the emission of the dipole antenna rotates in and rotates out, and depending on how fast the satellite will rotate, we'll have more or less fading signal where it gets stronger or weaker with time. Actually, from that signal level, we can then calculate on Earth how fast it rotates, but by this time we won't be able to do anything about it. So normally the way to deal with that is to have a protocol which carries enough redundant information to deal with fading, but in our case we have a very, very fine trade-off between the energy we have, the bandwidth we want to use, because as you have heard before, we want to transmit down pictures, and those take up a lot of space, and we only have 10 minutes communication window time. And on the other hand, because of fading, we need forward error correction, with is the kind of redundancy I've mentioned about. So basically you say words hello and then hello, and later so you hey, and you have information in multiple times, and you can calculate and recover the original sent information even if you lose part of it. Yeah, that's that. And we have basically two communication channels planned. One is at 2 meters. Those are the amateur radio frequencies we mentioned before, the classics actually, 2 meter and 70 centimeters. And one of those will be used for our TRX control uplink, which is also what we mentioned before, the emergency shut-off commando, which use DTMF commands. And the other one is basically where we transmit data. We have our beacon, which will be at the bottom of our 70 centimeters allocated frequencies band. And above that, we will have broadband on-demand data downlink, where we'll put down additional telemetry, the pictures, the noise data, and random messages, which we put up on the satellite before of that. So we also plan to do a bit of store and forward, not really, but basically to randomly, if we have the energy, to randomly transmit messages to Earth. Of course, the protocols will be free, so everybody can listen to it. Not everybody will be able to talk to it. So, DTMF emergency commands, yes. How are we going to save energy with that? Because we can't continue to listen, but we still have to. So we're doing the following. We're going to listen every 5 seconds for 200 milliseconds, and if there is a continuous DTMF tone, it will continue to listen, and then we can send our shut-off commands or whatever DTMF emergency commands reset we decide to implement. All right. Oh yes, of course. This is connected. The DTMF control is connected directly to the IHU. It generates one specially dedicated reset line, which shuts off and resets everything. So this is a hardware reset. Then the beacon. This is the satellite. I hear you. Will be in Morse code, CV, continuous wave. It will be sent for about every 60 seconds. It will last for at least 30 and will contain basic transmission, telemetry data, and of course our call sign, because we are on amateur radio frequencies. Also, it will acknowledge our DTMF commands in case there were any. So we have the start character. So this is the start of the beacon, the call sign, the beacon counter for Jupiter Larsen, which we implemented, basic bit fields, which tells us a bit of the state of the satellite, a number of commands, and if we still have some space, tokens, voltages, and parity. Then the interesting thing, how to transmit all the data. So what we planned was, well, you send a short command upwards, and then you get lots of data down. And this is basically what we're doing, but like I mentioned before, we have fading, so we want forward error correction. We want a standardized protocol that everybody can use and listen to, and we want high throughput because of the pictures. And to be quite frank, we haven't found the solution yet. So we have considered BPSK 1000, which is used on ARISAT right now. Probably we're going to hear later of that in Mario's talk. Looking forward to it, so should you. And we have also considered QPSK 500 with additional forward error correction. We have also considered before that RFSK with RX25, which is the standard amateur radio packet communication protocol, but I won't really, no, I will go in it. It has tons of problems. It has lots of overhead. RFSK is really slow, uses up a lot of bandwidth, and is not very efficient. And there are lots of fields and in RX25, in the AX25 header, which aren't used anymore. And the basic specification requires you to acknowledge every packet, which of course we can't do. We have satellite uplink, and it takes time to send stuff up and down. What you want to do is you send up, then down, and then you just listen, and the satellite should just transmit, and you have to listen. You do not want to acknowledge every packet. What you do is on the next pass, you say, okay, I didn't receive those 3 packets, send them again, but that's it. So we're still looking for it here in this case. Maybe, most probably, if we can manage, we might look into modifying BPSK 1000 for higher bandwidth. So that's one option right now. So how to avoid bidirectional communication? We already mentioned it, because what's the problem with bidirectional communication? You lose a lot of time and bandwidth if you have to wait for the acknowledgement, because you can't be sure the satellite actually received the acknowledgement, because you have a channel which is lossy, and okay, so you acknowledge a packet and then you don't get anything for 1 minute. Okay, maybe it didn't receive the acknowledge, send it again. You can't do that. That's just a no. So we just tell a satellite to send us whatever data we want, and then we just listen. What we do, we have different parts in the memory we want to download, and so we have several commands, and we just send this, after that send this, after send this, and then execute the queue. Of course, there's tiny bits of authentication in there, so to make sure the correct sequence of commands is executed. So now there we have the plan is that we have some regions where we have ground stations, people who have already agreed to help us, and they will send the commandos up when the satellite passes by. And then the idea is that multiple persons in that region will be able, that means you people, will be able to listen to our satellite and hopefully send back the data it received. And between several persons who have received the same transmissions, we hope to get error-free whole. Now, there are some regions where we do not have someone who can talk to the satellite and start it and tell it to start transmitting. And in that case, we have the wait until command, where someone says, okay, satellite, start transmitting this area of memory, this area of memory, and this area of memory. Then wait this many seconds, because we know the orbit by then and can say, okay, it will be in an area where, again, people can listen to it. And then start from the beginning and increment to the next area of memory and transmit that. So, and this is how we hope to get our pictures and our sound data down. Now, the hardware, where are we going to implement all that? So this is not the energy unit. This is just the main CPU. We will do TX-RX channel transmission. It's an ARM Cortex-M3. It's the same stuff you have on your badges right now, which is planned to be our main CPU right now. It will also do forward error correction, and it will do a tiny bit of image analysis, and it will trigger the camera, download the JPEGs from the camera, and talk to the flash and store stuff in flash. Also, it will do the alien counter. And of course, the microphone. How could I forget? It will sample data continuously whenever it has been started by the internal householding unit, sample a bit of data, store it, and save it for downlink later. So now, of course, we can't send every picture down. That's just too much data. We have 4 gigs of flash, and in the time, we will be lucky if we can get 10 pictures down or so. Maybe even that is optimistic. So we have to do some kind of in-place decisions on which pictures are worth downloading. And what we're going to do is we're going to look at the JPEG format, which stores discrete cosinus transformation coefficients. This is the way JPEG compresses pictures. And by just looking at the highest order coefficients, you get a kind of mini preview image, and from that we will generate a histogram or a compressed histogram, because we won't transmit back every colors for every picture, but we will transmit back information about the file size, which is very rough estimate about the information the picture contains. And so if it's only black sky, the JPEG picture will be pretty small, so it won't be worth downloading. On the other hand, there could be lots of noise in it, so it could be pretty large. In this case, we will look at the histogram. If the histogram is pretty even, very normal distributed, we'll say, okay, probably lots of noise, also not worth downloading. Now, maybe there's lots of blue in it and a bit of black. Oh, that might look like the Earth. Yeah, hell, we want that. Okay, even better if we would have, so we will get a camera which also already does JPEG compression. It might have, the best thing for us would be to get a camera which also does progressive JPEG compression, because then the coefficients will be right at the start of the picture. We won't even have to read the whole file. What we're probably going to get is a camera which doesn't even compress JPEG correctly, because it doesn't do CBCR compression, but does it for every RGB channel separately. But that's okay too. We'll just modify what kind of histogram we send down. So, to testing. Of course, we will test the satellite. We have actually a complete second team, which isn't telling us anything about how they are developing our tests. And they are right now looking into ways how to show us up. And probably going to do vacuum test chamber to see if our satellite is going to withstand space. Vibrating table, are we going to withstand the launch? Radiation will be ignored. And of course, we'll do a big balloon launch with the satellite to test our communications equipment. All right. And this is our tent. This is where we are hacking on the satellite right now, or at least on the hardware, not hardware part. And yeah, show by and ask us questions. Maybe buy a T-shirt, which we sell those here. And we are located in Leibandville, right over there, in the handle corner next to the big antenna, below the big shortwave antenna right here. So come over, talk to us, or drink with us. Okay, questions, please. Yes, please.
Can you take 3 antennas to be sure that one is always pointing towards Earth?
Excuse me?
You said you have 1 antenna,
Yes.
and it might be
It's
that the
a
satellite is
dipole
in
antenna,
position
yes?
that it don't send something to Earth. Can you take 3 antennas?
We could do a different antenna design. It's a very good question, actually. But the antenna design is the way it is because this way we won't have any problem with the ejection cylinder. So I'm going to do a demonstration with our model here. Our antenna is basically a measuring tape. So you also know measuring tape. If you do it around the neck and you put it out of the measuring tape roll, it's have it pass. It straightens by itself. And this is exactly what we want to do. When our satellite is ejected by spring mechanism by iOS in space, the antennas, the measuring tape will straighten up automatically. So of course we could put another measuring tape down there, but it would interfere with our antenna up there, and then who knows, it might get stuck in the ejection cylinder. So we don't really dare modify the design from iOS because we know this will actually they will actually be able to deploy. And we don't want it to get stuck in their prototype rocket. Yeah, but can we tell if the satellite is oriented to Earth? Well, we also plan, if we have the space, to include a magnetic orientation sensor. This might tell us if our satellite is oriented to Earth, and we might be able to decide not to send at all in that case. But then again, that's not a good idea because then during due to a software fault, we might not get any transmissions at all. So we won't do that. But we have another kind of sensor which I didn't mention. We also have photodiodes which will tell us which direction the sun is so that we don't take pictures in that direction since taking a picture in that direction would basically result in a glared picture, just white, and that's not useful. Okay, thank you. Next question.
Hello? Yeah. Okay, we have a question from the IRC channel. There's a guy who would like to ask you the following question. Would it be possible that you offer space to an SD card instead of sending hairs to the orbit? And if yes, is there any way to get FTP access to it via the built-in modem?
I don't think I really understood couldn't really hear the question, but what if FedEx fails? No, please again.
Okay, I read it again. Would it be possible that if you offer space on an SD card instead of sending hairs to the orbit? And if yes?
Okay. Well, the flash, it's not different from an SD card. Did you ask if we can get the SD card back to Earth?
No.
No,
I
not back to Earth.
I think I got it. Yeah, of course, it would be possible if it's not that much. Of course, we are carrying 4 gigabytes of storage up there, and it would be mostly empty when we launch it, and we won't be able to fill it up with all the data we are gathering in space. So it will be possible to send up data as well to space, except of hair, of course, if you just prefer data. But an FTP access would be quite difficult, I think, because that's limiting the amount of memory we can download from the stuff we want to gather. So we think that it's possible to download something like 10 to maybe 15 megabytes of data during the whole mission. So an FTP access is not really a good idea, because we would use all of our bandwidth for that and nothing for the
The only
data.
kind of uplink uplink data which is currently planned is adding additional messages to the random message transmission, and to modify some code maybe, but not much data. Thanks. More questions? Hit us. Or not in the physical sense.
Okay. Can you hear me?
Yes.
So you are trying to solve really many problems that almost every other satellite builder is trying to solve.
Yes.
And you have some nice experiments actually that you add. Why don't you go to some other people that already are launching a satellite and say them, take our 8,000 euros and put a microphone and a headphone in it, so you will have your experiment and they maybe already have solved some of the problems like orientation control.
Yeah, what's the fun to have someone else build a satellite for you? So.
Yeah, you are not launching it yourself either. So what's? I mean, you are not going to build a rocket yourself.
No, that's
so
true.
you are still putting up.
But at the end of it, we will know how to build a satellite, and then we'll have acquired the necessary knowledge to maybe do other things with it. So, who knows?
Okay. I'm just asking because I think there are already way too much satellites up there that do CV on a ham radio band and tell what temperature they have and try to get their batteries charged.
Yeah, that's true. Yeah.
Okay, thank you.
Thank you. Well, if anybody has good ideas we want to put forward, please come talk with us. We're looking for new inputs, definitely. So I'm looking forward to that.
So. Schön. So, are there any other questions now?
As the control commands you can send up to your satellite are not encrypted, would it in theory be possible to hijack the satellite or to reset it just to annoy you?
Of course it would be possible. Yeah.
Yes. Yes and no. We have, well, to be frank, we don't have a lot of safeguards against that, because we use amateur radio frequencies, and that kind of prohibits any kind of encryption. What we can do and are doing is basically three things. So the upwards transmission will be very narrow band. No, not narrow band, but narrow direction. So it will probably hard to listen to it. So we can, well, not hide secrets in it, but yeah, if it's some tiny part, like the DTMF emergency commands is not documented, you can still do brute force, but please don't. And and the chance that you will be successful in the 10 minutes it passes by is pretty low. And even then, we will be able to reset the satellite later. The other thing is, could you hijack the RX TX uplink and do something with the protocol, with the command queue? Well, the only protection we have of that is the message modification detection code, which will be sent at the end of the command queue. So if you looked closely, I'm too far, I've gone too far. Oh my God, mad scientist, I've gone too far. Yeah.
No, du bist schon wieder drüber gegangen. Ja.
There it is. Please step a bit to the side. So we are going to send clear command queue, then append command y excellent, maybe append command wait duration. There will be several commands, like send us the data of the image quality, they send us an image number such and such, dump the telemetry data, dump the counters, and at the end there will be execute command queue, number of commands I just sent you, MD5 sum over all the previous commands, and message authentication detection code, message modification detection code. Actually, this is not a MAC, this is MDC. This is wrong in the slides. And number of queues, MD5, this MD5, and if otherwise it wouldn't be a modification detection code, a password, which is only known to us and the satellite. So this is our tiny protection against that.
Excuse me, I'm part of this crew, and I have to make a small correction.
Come up.
In amateur radio, you are not allowed to do any encryption, but there is just one exception, and that's satellite uplink communication. So we are allowed to...
Pretty much, this is the exception.
Yeah, we are allowed to encrypt this, and we are going to encrypt this. So try it, it's not going to work.
Encryption is a strong word in this sense.
What?
Please don't.
Okay. One thing you could always do is put too much power on the satellite so no one else is able to do anything with it. But if that's fun, okay, we can't help, yeah?
Okay. If you succeed, okay, cool. Tell us about it.
So, any other questions? Well, it doesn't seem so.